proofs of laws of set operations. Now we are going to prove the laws of set operations of the complement class. So under complement class we are going to perform the part 1 under the advanced level. So under the advanced level we are going to perform the part 1 complement class. So here first complement law is of A union A dash is equals to universal set, that is mu, and the second complement law is of A intersection A dash is equals to the null set, that is phi. So we are going to prove these two conditions under the advanced level. Then now here, in order to prove this condition, so we have to assume a set that is nothing but A and a universal set and as well as the null set. Then now here, the complement laws we are going to prove these complement laws by means of the element wise proofs. So here the complement laws are of, one is of A union A dash is equals to mu, and the second complement law is of A intersection A dash is equals to phi, the null set. Then now the proof starts now. So in our proof, the first condition, we are going to prove the first condition, that is nothing but A union A dash is equals to mu. So in order to prove this condition, so here we must know the formula of A dash, that is A complement or complement of A. So here A complement is equals to, so here the complement of A, we are going to find out the complement of A or A dash. So here since we are finding the complement of A, that A must be subtracted from the universal set, that is mu. So here based upon this principle, so we are going to solve or prove A union A dash equals to mu. But here in order to prove this condition, first of all we have to prove that A union A dash must be the subset of mu and mu must be the subset of A union A dash. So here, in order to prove the condition that is A union A dash is equals to mu, so first of all we have to prove two conditions. So here the two conditions are of, one is of A union A dash must be the subset to the universal set, and the second condition as the right hand side must be the subset of the left hand side, that is mu must be the subset to A union A dash. Since we are going to find out, so first of all we are going to prove the first condition, so that is case number 1. So in our case number 1, so we are going to prove A union A dash the subset to the universal set, that is mu. Since we are going to prove it by means of the element wise, we have to assume an element which belongs to the set that is A union A dash. So here let that element be x. So here let x belongs to A union A dash. So here, so that implies since x is belonging to A union A dash, we can write the further logical step as x belongs to A. So here union indicates R. So here let us write the note. So under the note, union is nothing but R. We can represent by means of the V, which is the symbolic notation of the union or R. Then our intersection, which is nothing but the AND, so we can denote by means of the inverted V. So based upon these two symbolic notations, we are going to perform the proof. Then now here x belongs to A, so here union, that is R. So R can be denoted by means of V, which is the symbolic notation, and x also belongs to A dash. So x belongs to A dash. Then now the next logical step will be of, that implies, so x belongs to A or, so here we can write it as x belongs to, instead of A dash we can write it as mu minus A. So here as per the formula which we have considered here, so here A dash is equals to mu minus A, so I have substituted in the place of A dash as mu minus A. So I got this logical step by means of the reason. So here since A dash is equals to mu minus A, then now the next logical step will be of, that implies x belongs to A or, so here x belongs to mu, whereas in the next flower bracket, so here x belongs to mu, and here since A is removed from universal set, that is mu, then x does not belongs. So here since A is removed, we can write it as x does not belongs to A, but it belongs to only mu, that is the universal set, and x does not belongs to the set that is A. So x belongs to mu, so and x does not belongs to A. And whereas the next logical step, so that implies x belongs to A by removing the brackets, or x belongs to mu and x does not belongs to A. So here I am going to group. So here x belongs to A and x does not belongs to A together in the next logical step. So here that implies, so x belongs to A and x does not belongs to A, or x belongs to universal set that is mu. So here the next logical step will be of, so x belongs to A and x does not belongs to A. There is no meaning in this. So here I mean we have to, so here it dissolves, therefore only x belongs to mu is left over. So here x belongs to mu, that is a universal set. So from this we got the left hand side as x belongs to A union A dash. So here implies x belongs to mu. So here then we have the LHS is of x belongs to A union A dash. Then now that implies x belongs to mu is the right hand side. So from this it is clear that, so element x is present in A union A dash set, and the same element x is also belonging to the universal set that is on the right hand side. So here the elements of A union A dash are also the elements of the universal set that is mu. So from this it is clear that A union A dash will be the subset of the universal set that is mu. So here therefore A union A dash will be the subset to universal set that is mu. So from this it is clear that A union A dash is the subset of universal set. So we have proved the first condition. Let us consider this as the condition number 1 or the equation number 1. Then now, so we are going to prove the second condition, that is case number 2. So in our case number 2, we have to prove in the reverse manner that mu must be the subset to A union A dash. So here mu subset to A union A dash. Then now, in order to prove this condition by means of the element wise, so here we have to suppose one element that is x belonging to the left hand side that is mu. So here that can be written as, so here that implies x belongs to mu can be written as, whereas here we know so x belongs to mu. So I am going to write the same condition that x belongs to mu and x belongs to A or x does not belongs to A. So here I have created here x belongs to A or x does not belongs to A. So here, so that implies, so x belongs to mu and x does not belongs to A or x belongs to A. Then now from this we can write it as, so here that implies x belongs to mu and x does not belongs to A can be written as x belongs to, say here mu, it is belonging to mu, so x is present in mu but it is not present in A, so we can write it as minus A. So here A is subtracted from mu, so here we can write it as x is belonging to mu but it is, and x is does not belonging to A, so here or x belongs to A is written as it is. So instead of mu minus A, I wrote it as, so x belongs to mu and x does not belongs to A. So does not belongs to means we have to subtract A from the universal set. So in the next logical step, so that implies, so x belongs to, but mu minus A is nothing but A dash, A complement, or x belongs to A. So here we got this logical step by means of the reason, since A dash is equals to mu minus A, so here instead mu minus A, so here I have substituted as A dash. Then now the next logical step will be off. So that implies, since x is present in A dash or x belongs to A, we can write it as per the definition of the, so here union of two sets, that is A dash and as well as A, we can write it as, so here x belongs to A dash union A, or in other words we can write it as, so that implies x belongs to A dash union A as per the commutative property, we can write it as A dash union A as A union A dash. So from this it is clear that, so x belongs to mu implies, so x belongs to A union A dash. Whereas in the next logical step, then we have left hand side is of x belongs to mu, so that implies x belongs to A union A dash. So here from this it is clear that, so x is an element which is present in the universal set and the same element is also present in the right hand side set, that is A union A dash. That means the elements which are present in the universal set are also the elements of A union A dash. Therefore universal set that is mu will be the subset of A union A dash. So here therefore mu is the subset of A union A dash. So in this manner we have proved the second condition, and let us consider this as the condition number 1 or the equation number 1, equation number 2 or the condition number 2 which we have got from the case number 2. So here from two conditions, from equations, or in other words 1 and as well as 2, the first condition is of, so here A union A dash is a subset of mu, which is the equation number 1 or the condition number 1, and the condition number 2 is of mu is the subset to A union A dash. So let us consider this as the second equation or the condition number 2. So from these two conditions it is clear that A union A dash is the subset to mu and that mu is again subset to A union A dash. That means LHS is the subset of RHS and this RHS is again subset of LHS. From this it is clear that LHS will be equals to RHS. So therefore A union A dash will be equals to mu. So in this manner we have proved the first complement law, which is A union A dash is equals to mu. So here hence it is proved. So in the similar manner, let us prove the second condition, A intersection A dash equals to empty set, that is phi. Here the problem number 2. So in our problem number 2, we have to prove A intersection A dash is equals to the empty set, that is phi. Then now, since we are going to prove the A intersection A dash equals to phi by means of element wise proof, the proof starts now. So in our proof, let us suppose, let X be an element which belongs to A intersection A dash. Then now that implies X belongs to A, say here, and X belongs to A dash. Then now the next logical step will be off. So that implies X is belonging to A, and say here A complement, when we remove this complement, we have write here does not belongs to, and X does not belongs to A. So here X is present in A and X does not belongs to A. So here that means, so here X belongs to, certainly, so that implies X will belongs to the empty set, that is phi. So from this it is clear that then we have X belongs to left hand side, that is A intersection A dash, implies X belongs to phi. From this it is clear that the elements which are belonging to A intersection A dash are also the elements of the empty set. So here therefore the first set, that is A intersection A dash, will be the subset to this empty set, that is phi. So we have proved the first case. So here let us consider this as the equation number 1 or the condition number 1. Then now, so let us consider this as the case number 1. In our case number 2, so here we have to prove. Here we have proved, in the case number 1, we have proved A intersection A dash, the subset to phi. Then in the case number 2, we have to prove in a reverse manner, that is phi must be the subset of A intersection A dash. So here phi subset to A intersection A dash. Then now since we are going to prove it by means of the element wise, we have to suppose one element which belongs to phi. So here let X be an element which belongs to phi. So that implies, then now phi is an empty set. So here X does not belongs to the empty set, that is phi. So we can write it as, so here X belongs to A and X does not belongs to A. So here X is present in A and X is not present in A. So that means definitely X belongs to the empty set, that is phi. The set is empty now. So here A set A is now empty. So here we can write it as X belongs to A and X does not belongs to A. Then the next logical step will be off. That implies, so we can write it as, since X is belonging to A and X does not belongs to A, so we can write it as X belongs to A and X, when does not belongs to is removed. When we write it as belongs to, we can write it as the complement of A. Then the next logical step will be off. So here I have removed the does not belongs, then I wrote here I mean belongs. Therefore we have write here A complement. Then now that implies, so here since X is belonging to A and as well as X belongs to A complement, we can write it as per the definition of the union of two sets. So intersection of two sets, we can write it as X belongs to A. So here intersection A dash. So here from this it is clear that, so then we have left hand side is of X belongs to phi. Then now that implies the right hand side is of X belongs to A intersection A dash. So from this it is clear that the element X is belonging to the empty set and the element is also belonging to the A intersection A dash. That is, the elements which are present which present in the phi, that is empty set, are also the elements of A intersection A dash. Therefore empty set will be the subset of A intersection A dash. So here we can write it as, therefore phi will be the subset of A intersection A dash. So here let us consider this as the equation number 2 or the condition number 2. From two conditions, so here 1 and 2. So here then we have, or from equations 1 and as well as 2. So here the first equation is of A intersection A dash is the subset of phi, which is the condition number 2 or the equation number 1 or the condition number 1, and the second condition is of, so here phi the subset of A intersection A dash. So here let us consider this as the condition number 2 or the equation number 2. From these two it is clear that A intersection A dash is the subset of phi and this phi is again the subset of A intersection A dash, or in other words LHS is the subset of RHS and that RHS is also the subset of LHS. From this it is clear that LHS and RHS must be equal. So here therefore we can write it as, so here A intersection A dash will be equal to the empty set, that is phi. So in this manner we have proved the second complement law, which is A intersection A dash equals to empty set, that is phi.